Let's start today's class. This class will be the last class of this lecture series. Today we are going to discuss a property of a fractals, and we are going to calculate what kind of fractals uh, these logistic map create after multiple iteration. So we know that after multiple iteration and after and for a certain values of the parameter r, this logistic map becomes chaotic, and we have seen through the orbit diagram that for those values of r, the orbit diagram become very dense, and in that dense thing, what is the dimension of that dense thing? It is not a single point rather than a collection of points, so its dimension more than 0 but less than 1. Since it is not a continuous line, we cannot say dimension is 1, but and rather we can't say that this is a collection of points, and certainly it is not only the collection of points, it is more than the collection of points and less than a line. So the geometric structure of that orbit diagram or orbit at certain value of r, where we can say that there is chaos, there is the dynamics become chaotic on that region. What is the geometric structure of that things we are going to discuss here. So let me recapitulate what we have done in the previous class. We basically define through an example what the fractal is, and from there we have seen that the fractals has some three properties. So let me start by those properties, by stating those properties. So first property is that thing it is the first property that if there is some fractals, and if I zoom out a very small region of the structure, we will find some integrate complicated looking structure is also there. And if I zoom further, this structure we means whatever smaller region we zoom out, we will find some kind of structure is there. This is the first property of the chaos, which is in the opposite to the normal 2D plane. If for the normal 2D plane, if I zoom out a smaller region, I will find that no structure is there. It is become it is become more and more every times it's look like a plane. No no complicated structure is there. On the other hand, there is an example of that fractal, which is Cantor set. For the Cantor set, we have seen that if in whatever smaller region we zoom out, we'll found that there are multiple set of points, but those points are one apart from other by a different various kinds of gaps. So if I zoom out a Cantor set, you will find that all the points are separated by various kinds of gaps. So that kind of these gaps create a structure between those points. It is called the structure. And if I zoom out further, you will always find points which are apart from each other, and the gap is in the size of a different size, but this gap is quite symmetric, and this gap will be in the form of 1/3 that we have seen. And from there you will find the second property of that fractal, which is called the self similarity property. So in whatever region you will go, or in whatever smaller region you go, if you zoom out that whole smaller region, you will find the whole fractal in the smaller region. So that means fractals self similarity means the whole copy of full picture of the fractals is contained in the every smaller part of the fractal. So that is, it is self similar everywhere. That is why it is called self similar. But in it is not actually a property. The strict self similarity is not the property of the fractals. Rather, we can say if a geometrical object or geometrical complicated looking something, if it follows that it is self similar only in the statistical sense, that also count in the definition of the fractals. So fractals should have some self similarity property in itself. It can be statistical self similarity. And third is that the dimension of the fractals, it's just in contrary to the plane or a single line or 3D object, that for single line its dimension is 1, for 2D plane its dimension is 2, for 3D object its dimension is 3. In the contrary, for fractals the dimension is not an integer number, rather it becomes fractional number. So that is quite interesting, and that's why we are interesting to learn whether that we have seen the structure, complicated looking structure, or the complicated looking orbit for particular values of r, the logistic map become quite complicated. And if I see the orbit diagram, you will find a quite dense region, and the dense region we signifies, or we have means by numerically we have said that whenever we produce that orbit diagram, and whenever we got these dense region in the orbit diagram, we have said that the chaos, the orbit is chaotic there. There are dense set of points, and those points, as I have said in the beginning of this in the today's beginning of this today's class, that those dense set of points is neither a continuous set of point which we can characterize by a single line, or we cannot say it's just a say we in the on the other hand, we can't say that this dense zone is the collection of few points. So that's why it is interesting to see that whether or not it is a fractional dimension. And we know already that these region that are infinity, that is that we know that from the period doubling root of bifurcation. So every period double, every point will period double after varying r, and finally it become infinite period double. So we know that these points are self similar. We have seen in the by renormalizing, and we have seen some very interesting universal thing, and we have seen that this orbit diagram is self similar to itself. So this self similarity is there. The complex looking structure is there, because the every time you will plot this orbit diagram, you will find that the fork like a twig like structure is appearing, reappearing, and reappearing. And if you wherever means if you go in a smaller part of the whole orbit diagram, and if you zoom out it, and we have seen it numerically in computer, that if we zoom out, it will look exactly or statistically same, or exactly same to this counterpart in the whole part. So what I am saying, let me, so these, okay, so we have drawn computer in computer that this orbit diagram. So it is every orbit is doubled after some value of r, and it's again doubled, it's doubled, and same structure is, and you it doesn't matter whether you take this part, if suppose that this is part, the whole part, so this is the whole part. However, if I go in any uh, smaller part of this, you will find that same kind of structure is there, because this period doubling thing will going on, and it will become the infinite period double points, and when infinite period double, it will become exactly self similar. So in R infinity, where infinite period double happen, period double happen, then you will find that if I just take smaller part, and if I zoom it out, you will find that the inside that region, the whole uh, orbit, or whole orbit diagram is there. So that's it. So these two properties there. So one is structure is there, and two is self similarity is there, and we want to check whether or not the third property is satisfied, that is its dimension is fraction or not. So that's why we are developing a method from which we can calculate the dimension. And what we have seen, that there are two concepts of dimension for exactly similar object. We found that the similarity dimension, and by using the similarity dimension, we have determined the dimension of this Cantor set and this von Koch curve. And after that, we have seen that if that thing is not self similar, then what how can we define the dimension? Then we have again introduced a concept which is called the box dimension, and by which you see that we can measure that dimension of any object, and also fractals. And we have we have just checked that whether the box dimension of the contour set and the similar dimension are same or not, and we have figured it out that the both are same. Now let's go towards the critique of the box dimension. Critique of box dimension. Now, what is the problem with the box dimension? So the first problem is, okay, let me rejoin this meeting. Yeah. So what is the critique of this box dimension? So first critique is, and which we can solve, that if you recall that whenever I just want to count the number of box which actually minimally cover the my geometrical object, we have to find this minimal cover of the box. What is the minimum size box? For the luckily for contour set, we know this minimum size is 1/3 to the power n. For in the nth iteration, we know, means when we actually forming the contour set, we know that at the nth level it is not a contour set. At infinite n equal to infinity, it become contour set, but at the nth level we know this minimum cover will be 1 by third to the power n, one the minimum length, and 1 by third to 1 by 3 to the power n kinds of things are there, 2 to the power n number of objects are there. So if you want to cover the whole contour set by this minimum cover 1 by 3 to the power n, you need 2 to the power n copies of the smaller size of box whose size is 1 by 3 to the power n. And since we are lucky enough that we know what is the minimum cover. That that's why it's become very easier to calculate the box dimension of the um, contour set. However, in general we can't find in general we can't find the minimum cover. And if I can't find the minimum cover, you will find that the some part of this object is out of the box, and we can't cover these things. So that is the one problem. But it could be solved by, if we consider a smaller size of box, rather smaller size of box, and if we count how many box is required to cover the whole the object without considering or without thinking much about what is the minimum cover. If something is hanging out there out of the box, what we will do, we'll found a smaller size of box which actually cover this. And for this smaller size of box we want to cover the whole structure, and at last we found that how many such smaller box is required to cover whole the structure. That's why we can solve it by smaller size of boxes. So that's how we can solve it. Now in these things also there is a problem. The problem is, second problem is, if I do so, so what you will find that the dimension of the rational number between 0 to 1, the dimension of the rational number between 0 to 1, the box dimension actually, the box dimension of the rational number between 0 to 1 will be 1. But this is not true, because we know that if the dimension is 1, in between 0 to 1 there should be uncountably many numbers are there, uncountably infinite numbers should be there. That's why we can say this set is continuous and its dimension is 1. But we know that rational number is countably many. The set of rational number is countably many. Countably, and it's not uncountably many, but it's countably many. So that's why its dimension could not be could not be 1 is equal to 1. It should be always less than 1. So that's why the box dimension gives us the wrong kind of information and wrong intuition. So that's why box dimension is problematic, and we could not means often we can't use the box dimension. And apart from that, to find the smaller size of box, it's or count this smaller size of number of smaller size of boxes, it require humongous amount of effort, computer effort. That's why we actually don't use the box dimension to say about or to determine the dimension of a fractals or a complicated looking structure. So that's all. Now is it the end that we can't do anything with a computer or numerically to calculate a dimension of a complicated looking structure? No, it is not. There are another kind of dimensions which are called the pointwise dimension and correlation dimension, and these concept of dimension are very friendly with the compute numerical approach. With the numerical and with the help of computer, very easily one can find out these kind of dimensions, and these dimensions are very close to these box dimension and those kinds of dimension. And we can think that uh, these dimension are actually the fractal dimension of the fractal it's actually represent a concept of the dimension for these complicated looking objects. So let me introduce pointwise dimension. let me introduce pointwise dimension. Hmm. So for that, let me draw one. Suppose in the 2D plane, or maybe not, I will going to 2D plane. Let me draw 1D plane. Okay, and in the vertical line I am drawing, because okay, let me is x n plus 1, and suppose this is xn, or maybe let me draw it. Suppose we are starting, this is x, and suppose this is, we are starting at excuse me, from, suppose this is, I am drawing the orbit of logistic map in a R where chaos exists. Suppose this is x0. If I start from x0, what kind of points I will getting? So I will find here is a dense set of points will be there. A dense set of points, apart from different sizes, I will get a dense set of points. So this is the thing I will get here. This is the orbit of the logistic, means don't confuse. So what I am saying here, so suppose that is x0, and if I iterate by this logistic map, I will get x1. I will put the x1, suppose x1 is somewhere here, x1, it is x1. Then I will put again the x1, I will get x2. I will x2, x3, I will x3, I will, if I put x3, I will get x4, x0. So x1 is equal to r into x0 into 1 minus x1, and if I put x1, and the value of x1 I am plotting here, and then again using x1 I will get x2 and plot again there. And since it is chaotic, it will never settle down to any singular set of, means any orbit. It actually rather since because of the property of transitivity, we know it will become very dense, the orbit will become very dense between 0 to 1. That's why it is a dense looking point. That much we know. Now we want to calculate the pointwise dimension. So pointwise dimension means, suppose we are taking some part of this, suppose this to this part, suppose this part is epsilon length. So first we will calculate how much point is there between, okay, how many points are there in between this epsilon length. Suppose you will find that, suppose this is point x, suppose this is a point xn. So in around xn, within the radius of epsilon, how many points are there? So you will find that n x epsilon. So within this epsilon distance of a point x, how many point is there? N epsilon. Now if I increase this epsilon, suppose rather than this, if I consider this much is now my epsilon, this much is my epsilon around this x, I will find another, this suppose epsilon 1, this suppose epsilon 2, I will find nx epsilon 2. So this I will find, and it is obvious from here that this if I larger the radius of this region, or this length of this region, the number of point it will include inside itself will become larger. So that means it should, and if now if we vary and if we assume that the nx epsilon the number of points that will be there, the number of points will be there inside a epsilon length will be nx epsilon is actually proportional to this epsilon to the power d. So if it's proportional to the power epsilon to the power d, then we can say that d is the dimension. So why I am saying this d is the dimension? Because you see this is a thing for the from the intuition. So if suppose there is a cube and inside the cube, if you how much point you can means how many means point you can means or if you assume means if you consider or if you imagine that smaller size of marbles are there, very smaller little sizes of marbles are there inside a cube, so how many such marbles will be there? So it should be proportional to its volume, right? The number of marbles of suppose the length epsilon is actually suppose this length of the cube is one arm of that cube is epsilon, then it should be proportional to the volume. And if I increase, it's also increase as the volume increases. So you see this n epsilon should be proportional to the epsilon cube. So that's why this cube, the number of marbles inside this volume will increase at epsilon to the power cube. So this cube is not an accident. This cube is actually showing or the cube is coming from the intuition of this dimensionality. It actually it tells what is the dimension of that geometric object where I am putting the smaller size of marbles. Now in place of marbles, if you consider, if you can consider or if you can think or imagine that small very points are there. So with the points also same thing should be there, same kind of intuition if you can form, and that is enough. So from there we know that these if we can calculate what is the proportionality means what is this how this number of the point vary with epsilon, we can find out the dimensionality, and this dimensionality this d is called the pointwise dimension. Pointwise, why pointwise dimension? You can see that how much means it depends on the how many points it contains. So that's it. Now you can means it is very obvious that the number of points actually this dimension actually vary or the number of points will different. This number of points is different. It depends actually number of points should depends on the this x. So from where I am means whose in the whose neighborhood I am collecting the points, it's actually going to matter much because here if I imagine this suppose x, now in neighborhood of okay, suppose you are considering this point, so in neighborhood of its epsilon it will become so epsilon by 2 here and epsilon by 2 here. So here so only the point that will contain is not actually whole epsilon. In the epsilon by 2 there will be 0 point, and if I this is suppose this is the center of the radius, then center of the radius at 0 only epsilon by 2 length is there. So that means around this point 0 there will be less point than if I consider the center here. So that's why it depends on the point which I am taking as center. So this is called x. So this is now if we can handle this problem with saying that if I now what I am saying is called the pointwise dimension at point x and around point x. Now to get an overall dimension, to get an overall dimension, of these complicated looking dense points, one could average averages over nx epsilon over many x's, many x, and the resulting will be that the average number around many x, that should not be depend on this x, because I averaged out, or if I count, suppose I take here from here 100 such x's, and if I average over x's, means how many on average, if I take any arbitrary point, average actually telling us if I take any arbitrary point, and what will be the on average number around means if I take, if I choose a randomly pick a x between the 0 to 1, then I draw inside a box with length suppose epsilon. Now if I ask how many point will be there, so that will be c epsilon, that should be proportional to the sum d, and this d is called correlation dimension. Now how we will find that geometrically? So if I plot this log of c and this log of, if I plot this ln c versus ln epsilon, so if you can find out that it should be like this kind of structure. Why so okay, this kind of structure? This kind of structure, because if you take ln c, it will be some constant plus d ln epsilon, so it will be a straight line. But why this flattening line will be there? Because you see here, if your cover is 0, epsilon is 0, the radius of the cover is 0, then it will contains no points. And if you increase the cover, you will find there are very small number of points are there, until you actually get a minimum the value of minimum cover, then you will not find, until then you will not find any point inside. So that minimum cover is, this is the minimum cover, this is epsilon, and if you now increase the minimum cover, what you will find that if it has a maximum cover, suppose here if I take epsilon equal to 1, so inside this cover 1 you will find the all of the points are there. So if I increase instead of 1, if I take 2, that value of the epsilon is 2, you will find still there will be how many points are there? Same number of points are there as it's in the cover of 1, because outside this epsilon equal to 1, there will be no point. So if I take epsilon equal to 2, suppose epsilon equal to 2, if I take epsilon equal to 2, this is suppose epsilon equal to 2, that the number of points that is contained in epsilon equal to 1 and that is same. That's why if I change the epsilon, the number of point it contains will not change, so that's why it will flatten. So that's how you calculate the correlation dimension. Now let's us calculate the correlation, the exact correlation dimension with using computer, the logistic map. So let me write the question here. So consider the logistic map xn plus 1 equal to r xn 1 minus xn at the parameter value r equal to r infinity, which is equal to 3.5699,456 corresponding to the onset of chaos so that the attractor is a contour like set, although it is not strictly self-similar. Then compute its correlation dimension numerically. And whenever I actually say this correlation dimension, it's we will calculate it numerically. On solution, to visualize, let's form the thing by let's form the orbit diagram. So suppose from here, then these two, and suppose again this is the orbit diagram. If I increase r, these are going to happen. Now what does this mean? So this is, I am varying r, let me, this is r and this is x. So at if I start some from particular x equal to half, suppose here, so this is the point. So now at r equal to something like that, less than 2, we know here in the line only one point will be there. Okay, let me draw it properly. Okay, now you see this is x-axis. Suppose this is x-axis, where what is the orbit. So this is this is corresponding to a stable fixed point. And if I say what is the fate of the system, so you'll find that the fate of the system after some iteration, you'll find the system will be always be at this point corresponding, suppose this x and same is that. So that is fine. Okay. Okay, that is fine, no problem, no problem is there. Okay, now at if I increase, suppose this is r0, suppose this is r1, and this is r1 where the bifurcation happens. Now after bifurcation you will find that this point actually these points becomes these points bifurcate. The stable fixed point, stable one fixed point bifurcate into 2 points, and the stable orbit becomes a stable periodic orbit. So this 1 point become 2 point, and this 2 point become 1. Okay, now it is fine. Now go further. Okay, now if I go here in this region, suppose this is r1, this is suppose r0, and suppose this is r3. Now we find that every single point is become again 2 periodic point, 2 point, every point become 2 point. Here this point also become 2 point. Now let me do this further one. Now the same thing is continuous. This is r2, so this will be r2. Now this is will be r3, suppose this is actually r3. Now here every point becomes 2, so these and these become again 2, then this point become again 2, then this point become again 2. So that means 1 2 3 4 5 6 7 8. So now you find that at r3 8 points are there, and this number of points is same as the previous one in the like contour set. And here you find that the points are there with gaps between them are in various sizes. So the gaps between here and here and here, and so sets of points actually increases in terms of 2 to the power n and 2 to the power n. And what you find that these points becomes the number of points becomes large, number of becomes high, and it also the size the gap between the 2 points become it's actually various sizes. So if I go these times at infinity, at r infinity, you will find that r infinity the infinite numbers of points are there, which is like contour set. Contour set contains infinite number of points, and the points, the distance between 2 points, the gaps between the 2 points are at the various sizes, and we will actually find here also the gaps between the 2 points also various sizes, and the only difference is the gap between the 2 points here. Actually you can't, this is not regular, the gap between 2 points are not regular, but in the contour set the gaps between the 2 points is actually multiple of 1/3 to the power something. So that is the basic difference between the contour set, but the similarity is there, that each contain infinite number of points which are apart from each other through the gaps of various sizes. So here also you will find one, the infinite complicated looking structure at arbitrary small scale. So if I take any smaller size, any smaller region, and if you zoom it out, you will find that there are infinite numbers of points are there, and the distance between 2 points are different, are in the various sizes. So that means inside of a very smaller region the structure is there, and second, it actually it's similar in statistical sense, and third, we are actually want to calculate its correlation dimension. So to calculate its correlation dimension, let's use the let's use the computer. So two properties are there, the structure is there, structure at smaller scales are there, two statistically self similar, and third, the dimension we want to see. Let's see. Okay, let's calculate. Oh yeah, it comes that its dimension, so this is ln log epsilon, this is log c epsilon. So if I plot it, you will find that it is a straight line and its slope is 0.494, and if I go here, so you find that the slope ln c equal to k plus d ln epsilon. So if I plot ln c versus ln epsilon, the slope is actually d. That means the slope is the dimension, and so dimension, we find dimension of the logistic map. Dimension of the logistic map is 0.494, 0.494. Here the logistic map I am using, the value of r I am using are equal to 3.5699456, and I started from the initial condition x is equal to half, and I find that dimensionality is less than 1. So that is our intuition is true, that these dense orbit, these the dense point, this is the set of point, it becomes denser and denser when we are going towards infinity. So that it says that at the onset of the chaos the infinite points are there, and these dense set of points is just not only the collection of points whose dimension is 0, and it's not also the continuous sets of points which creates a line, and the dimensionality remain between 0 to 1, it is near about 0.5. So that the three properties there, the dimension is less than 1, fraction, and again fraction, statistically similarity is there, and structure at smaller scale. So this makes exactly looking like, means not exactly but looking like the contour set. So we can say it's topologically similar to the contour set. So that's it. So now we know that where these chaotic orbit settle downs, that means here this is the chaotic orbit, this is the chaotic orbit settles down. So now we know the chaotic orbit settle down to a very complicated looking structure. It's not a line, not a complicated set of point. It's a it's uh, settled down to a strange kind of attractor, which I am not going to elaborate in this course. Is called strange attractor. It is strange because it's not a point collection of points, and not a line, rather than in between two. So in between dimension 0 and 1, its dimension is 0.5. The complicated looking structure, or the strange attractor on which the whole orbit will going to settle, or the whole chaotic orbit will going to settle, is a strange attractor whose dimension is less than 1. That means that becomes a fractal. So that's it. So that's it. There is I'm not going further in this chaos and fractals. So I think this is the end of the class. So thank you for joining in this course. So thank you. I'm quitting this lecture now here.